So, guys, just let me ask you this. Well, what's the advantage then of foam fractionation over some of those other technologies we've discussed, say GAC and ionised resins and so forth? What's the advantage over foam fractionation?
Sure, mate. Well, I mean, maybe, we've got a table up at the moment that runs through some of the key ones, but I think what's important to point out is not just the advantages, of which we think there are a number, but also some of the disadvantages. So as we sort of alluded to, it doesn't work on short chains. It shouldn't be considered a technology for complete removal of short chain compounds. It works extraordinarily well on long chain compounds, and we'll get those down to below drinking water guidelines beyond detection limits at times. So it goes very well, but in that C1 to C4 range, there's mediocre performance. C4, C5, it gets a little bit better, but C6 and above it goes well. So it's important to know that when you're sort of putting it into context with these other technologies. Scalability, so they're sort of moving our way through these, like it's infinitely upscalable. I mean, if you imagine what we just saw down there at the Williamstown lab, but the size of a grain silo to treat huge volumes of water, that's entirely feasible. And there is no indication that scaling the process up has any impact on the efficacy of foam fractionation. In fact, to the contrary, Dave and I, after yesterday's presentation, were pouring through the results from Oki, and those are 2,000 litre, 500 gallon vessels, of which we have 5 of those in a row that we'll see a little bit later, and those systems are getting it down to below the detectable limits for a lot of those longer chains. So it's quite a large system, and we think that's certainly we could get as big as we needed to.
But the other systems are all scalable as well.
Of course they are, yeah. So both GAC and resins can be scaled up to size. So that's great. That means they can all work contiguously to achieve a good outcome. One of the big advantages we think at the front end of the foam fractionation process is its ability to manage co-contaminants, and particularly hydrocarbons. Like for those, I'm sure a lot of people in the audience would understand the process of air stripping for removal of dissolved and hydrocarbon compounds out of solution. This operates in a very similar way. A lot of the contaminants, including some of the metals, will actually rise up with the PFAS compounds and accumulate in that foam. So in that single mechanical physical separation phase, we're actually able to strip a lot of the contamination out. And I think that's fundamentally important, because one of the things that resins and carbon don't do well is they have a certain number of available sites for absorption and for removal of contaminants, and some of these resins are quite targeted towards being effective on PFAS. But if you flood them with hydrocarbons, if you flood them with some of the other co-contaminants, calcium carbonates and all sorts of things start to come into that solution, then you're going to compromise those resins. Those products are quite expensive. They create a large waste stream, and so
it's not that they're not as effective; they just become saturated.
Oh, they work really well. Don't get me wrong.
No, but with those co-contaminants, they become saturated early, or is that the issue with it?
Correct. So if you've got these contaminants, and even down to just suspended solids and even dissolved solids, they'll start to take up sites on the resin. Now, when you've got quite a lot of cost invested in your resin beds, and you've got a limited amount of bed volumes that they can handle, and you start to blind the top of those, you'll get channeling, you'll get all sorts of compromises to that. So we're able to strip that out early.
So foam fractionation is really a gross pollutant removal system, whereas resin and GAC are a lot more sensitive to water chemistry that's coming through it.